Hello and welcome back to the lab. Today what I have for you is a quick demo showing off real-time decoding of 100baseT1 automotive Ethernet using a ThunderScope and ngscopeclient. So here's a quick overview of the setup. Sorry for the spaghetti, I'm a little bit tight on bench space, but we've got the ThunderScope over here with the 4 inputs connected to this test fixture right here, which has a pair of dual directional couplers that take in the 100baseT1 Ethernet signals from either side and then bridge the forward and reverse paths as differential signals out to the scope on either side. And then the signal is being generated by a pair of these media converters, which are just going from 100baseTX on one side to the automotive 100baseT1 on the other side. So here we are in the filter graph editor. There's a lot to unpack here, so we're going to zoom in a little bit closer and take a look at it piece by piece. Starting at the input, we have channels 1 and 2 form one of the differential pairs coming off the test fixture, so we subtract these, and that gives us the differential measurement. And then channels 3 and 4 are coming from the other differential pair, and that's also being subtracted, giving us another differential measurement. Now, if you're not familiar with automotive Ethernet, it uses a single pair to transmit and receive. Both sides talk over each other and use hybrid couplers within the PHY to separate the transmit and receive signals. If you're doing a mid-span tap as we are here, you have to use a dual directional coupler. And the problem is that real-world couplers never have perfect directivity. There's always a little bit of leakage from the forward path into the reverse, and they're also not going to have perfect frequency response. And so what we have here is the coupler de-embed block. It takes in a pair of inputs from both sides of the dual directional coupler, as well as the 4-port S parameters of the coupler. So it will not only correct for flatness in the forward and reverse coupled paths, it will actually also, because we have both paths and we have the S parameters for the leakage, it knows how much of the forward path signal is leaking into the reverse coupled port and vice versa, and so it can actually remove most of that crosstalk and give us significantly better isolation than if you were just measuring directly at the coupler. And moving down the signal path, the next step is just a 3 dB emphasis filter. This is just removing some of the ISI in the signal and cleaning it up a little bit. And then upsampling from the 250 megasamples per second coming off of the ADC on the scope up by a factor of 4 to 1 gigasample so that we get better eye patterns and have a little bit more samples per UI. And before we can do much else with the signal, we're going to need to recover a clock. The regular ngscopeclient clock recovery PLL filter expects a NRZ signal and will internally find zero crossings for an NRZ signal. But because we're dealing with PAM3, if we go back to you can see that we've actually got multiple level crossings here. And so right here, for example, if we've got at the -1 state, if we're transitioning to the 0 state versus the +1 state, we're going to have a different slew rate. And so we can't just threshold at the midpoint of the eye crossing here, for example. So if we were to threshold from the -1 to the 0 state and transition here, we are nowhere near the midpoint of the crossing going up to here. And so we're going to end up essentially adding jitter to the recovered clock just because the edges are not the same rate. And so we actually have a dedicated block for PAM edge detection. You can tell it what the nominal level of each code is, or in this case, there is a auto level feature that will automatically determine the positioning of the eye. So it looks like we've got about 8 millivolts of DC offset on this signal. And then it will find the level crossings more precisely and then feed that into the PLL. And the PLL then outputs both the recovered clock that we can use along with the data to display the eye pattern. And additionally, it also outputs the sample data on the clock edges that we can use for upper level protocol decoding. And so what happens next is we're taking the sample data from the CDR PLL. This is still the sequential PAM3 symbols on the clock edges, and demuxing it into separate I and Q streams. This is not actually QAM, but because 100baseT1 uses a 2D PAM3 constellation, we're using the same block that we would if we had I and Q coming in sequentially out of some sort of other data stream. And so then coming out of the demux block, we've got separate I and Q signals, and we plot that as a constellation. We decode the Ethernet, and then feed that into the IPv4 protocol decoder. And now going back to the main waveform view, we can see we've got the eye pattern, we've got the constellation, we've got the packet list, And then on the timeline, we can go and zoom in on one of these packets. And we can see this is a Ethernet frame to one machine from another. It is IPv4, and we've got the IP address there and the header checksum and a bunch of bytes of data. And if we go over here, you probably recognize this as a Linux ping packet with the sequential payload starting from 0x10. And before we wrap up, I'm just going to clear everything so you can see how fast things update. 250 megasamples per second, 20 million points, coming in at about 12 waveforms per second. It hits 12 and a half when I don't have the screen capture running. The GPU bogs down just a little bit with the video pipeline running as well as ngscopeclient. But since I cleared, we're already at 20 gigasamples integrated, 1.5 billion UIs integrated, and that's in just a couple of seconds. This is the full 1 gigasample per second off the ADC being processed in real time on the GPU with the de-embedding, the clock recovery, the protocol decoding, everything in real time on the GPU. Thank you for watching, and I hope you enjoyed.